Good afternoon. Welcome to CSCE 317, Computer Systems Engineering. I am Jason Bakos. I know some of you. Welcome. Hope you all had a good break and had a chance to relax. So joining me, I'm going to have two graduate teaching assistants this semester, one of whom is right here, Charles Daniels.
Hello, everyone. Hey.
I think many of you might know Charles, right?
Definitely seen some of you all around.
And the other will be Philip Conrad, who is not here, but hopefully he'll be here in 2 weeks. So the syllabus starts out with the catalog description, system level modeling, evaluation of computer systems requirements, elicitation, specification, architectural design, reliability, performance evaluation, Markov modeling, lifecycle cost analysis, project management. So there should be an asterisk here because for the past 20 years or so, this class has been taught basically like an applied statistics course, right? Charles, is that accurate?
When I took it, it was basically like Stat 509 plus computing theory, so yeah, I'd say so.
Yeah, so there's a lot of overlap with statistics, and there wasn't any hardware design. So based on feedback we've gotten from students and also from the agency that accredits our programs, ABET, the department decided to make a dramatic change to this course starting with this semester. And basically they brought me on board to redesign the course to make it similar to my other two courses, 611 and 313, for those that have taken one of those courses or heard about them, where basically it'll be a lab course where we'll spend a lot of time in the lab actually building stuff, building computers. So the description is not very accurate, and starting with next year, this course will actually cease to exist. It will become CSCE 491, Computer Engineering Capstone. So this will become the new hardware capstone course. So this semester, it's the first time I've taught it, and it's kind of experimental. So it should be an interesting semester. So the whole class will meet on Mondays here. And then if you're in section 1, you will have a lab on Wednesday, same time, but in Swearingen 3D22. And likewise, if you're in section 2, your lab will be same time on Friday, also in Swearingen 3D22. Charles will be in the labs on Wednesday, and Philip will be in lab on Friday. And I may or may not be there depending on how busy things get, but I'll be giving the lectures every Monday. Does that make sense? If you're in section 2 and you'd like to get some time with the TA outside of office hours, you could come on Wednesday if we've got enough desks, which shouldn't be an issue, right? And vice versa, right? Okay, I post everything on Dropbox or the departmental Moodle site, dropbox.csc.sc.edu. Right now, both sections are on there, but by the end of this week, we'll be merging both sections into one Dropbox site, okay? So I think I've got stuff posted on there right now for section 1. I have to copy that over to section 2. I'll do it right after class today. So if you log in, don't see anything in there, it's because you're in section 2, but I'll have that fixed by the end of the day. The textbook is this one, Embedded System Interfacing by Marilyn Wolfe. We're not going to follow this very closely. It'll mostly just serve as a reference material. So so don't expect to have to read it. We'll be providing a lot of material online, and in fact, we're writing our own textbook. So the material that we build up throughout this semester will eventually go into one of our textbook for this course. So there'll be a lot of stuff posted on Dropbox. Make sure that you're receiving your emails though. So I often will post announcements. Me and the TAs will post announcements on there that get emailed to everyone. And you know, sometimes it's, we'll push a deadline back or something like that. So there's some important information there. Make sure you get those emails. Okay, the course learning outcomes, section 5 on the syllabus. These are unofficial, pending the change over to CSCE 491, but these have been updated. So the objective is we have 5 different outcomes, mostly involving writing low-level software to do software-hardware interfacing and developing embedded software on a low-power platform. Important dates, we've got our first classes today. We're going to cancel lab this week. So you don't have to come to lab on Wednesday or Friday. And then next Monday is Martin Luther King Day, bless you, is a holiday, class is canceled, and so the labs will also be canceled next week. So you don't have to worry about coming back until 2 weeks from now where we'll meet here. And by that time, you know, we'll have enough stuff ready for you to start working in the lab. Make sense? Okay, so we don't meet again for another 2 weeks. Let's see. Spring break, March 9th through 13th. The withdrawal date is March 28th, which seems pretty late, but that was what it said. The last lab is April 22nd. Last class is April 27th. The project cutoff date is April 28th, which is reading day. And I'll talk more about that in a minute. And the final exam is on May 4th. I've got my contact information there. My office is in the Story Innovation Center, Innova. Is that how you pronounce it?
Yeah.
Whatever, the IBM building. Yep, 2213. Both TAs are in my research lab, which is right catty corner to my office in room 2236. Charles will be available for office hours Mondays and Wednesdays at noon, and Philip will be available for office hours Tuesdays and Thursdays at noon. And then for me, you know, I'm pretty flexible. I mean, if I'm in my office, you're welcome to come in and ask questions if you need to. So this course, yeah. So oh, by the way, there's a combination lock on the lab. It's 51213. I've got that on the first page of the syllabus, and it's also here on the lecture slides, which I'll post on Dropbox. Okay, so this class will have 65% of your course grade will be based on the project work. Projects will be in teams of 2, unless you really want to be in a team of 1. But we encourage you to find a partner who's ideally in your same lab section, although if not, we can work around that too. So the project scores will be shared by both members of each team, which means that 65% of your course grade will be shared by shared with your partner. The remaining 35% of your grade will be based on individual grades through the quizzes and the final exam. So the quizzes will have in-class quizzes and online quizzes through Moodle, which will comprise 20% of your grade, and the final exam is 15%. So as you probably know by this stage of your career, whenever you work in a team, it is almost never the case that both members of the team contribute equally, right? It's difficult to do that logistically, right? And there's different personalities and all kinds of other practical concerns. So these individual grades are designed to, you know, differentiate the two members of the team, right? Make sure that both partners are contributing at least enough to understand the material. The projects will be graded based on a demonstration. So your group will demonstrate each project to the TAs at some point, as well as with a report. They'll be writing up a lab report. You'll also be submitting your code, but I found that in a class like this, it's difficult to grade based on code, especially when it comes to assigning partial credit. Like for example, if your code doesn't entirely work, it's difficult to. Sorry, my watch is freaking out. It's difficult to assign partial credit just by looking at code. So we'll mostly be doing these, grading through demonstrations where you may bring up your code and point certain things out, but also be looking to see if your design is working, right, in class with the hardware, at the bench there. And also there's a lab report where you'll be, writing a short report summarizing what you did, and in some cases, putting in results, experimental results, like performance results, right? And doing some sort of analysis, okay? All right, sorry. Let's pause. Okay, all right, so any questions about that? You'll still be submitting your code through Dropbox, obviously. So you'll submit your code, which we have scripts that run it through MOS to check for cheating, but your grade will be based on the demonstration and the report. Okay, so what is this class all about? Well, like my other two classes, 611 and 313, this course is fundamentally about embedded systems. Are you familiar, any of you heard of that term before, embedded systems? So some of you have taken a few of you have taken 313, I guess. An embedded system is a computer designed for a specific purpose. In general, it's any computer that was not intended by its manufacturer to have the user reprogram it, right? In other words, it was not intended to be user programmable. It's a sort of for a single application. It's a computer that ships with software that's not changeable by the user. Right? But every embedded system and every embedded computer has to strike some kind of trade-off between power consumption and computational performance or throughput. Right? So there's a desire to minimize the amount of power consumption required by a computer. But depending on how much performance you need, you're sort of locked in. So there's sort of this spectrum between, as you go, less power consumption, less performance, and more performance, more power consumption. So in general, processors will range from milliwatts with 1 to 10 milliwatts with 1 to 10 million instructions per second, all the way up to 100 watts, 10 to 100 watts with 10 to 100 billion instructions per second. So looking at actual systems, this would span the range of like a light-up greeting card or a toy, all the way up to like the computer that controls the autopilot in a Tesla, right? So each one of these systems has this trade-off, and the more performance you need, the more power consumption is required. In this course, we wanted to focus on lightweight, low-power embedded systems, and we wanted to have a platform that we can use that you could write your code for and to actually build out, add peripherals to. So we had to make a decision, and it came down to the two most popular and widely used embedded systems that are used for this purpose, for hobbyists and education, and that would be the Raspberry Pi and the Arduino platform. You guys heard of these? You guys have used Arduinos in 211, and you probably heard of the Raspberry Pi, right? So both of them are about the same size, and strangely, they both cost about the same, but they are drastically different. The Raspberry Pi has 4 64-bit processors on it. And the Arduino has, or most Arduinos, this one, we're basing this, there's different processors that you can put on this form factor, but by far the most common one, and the one most people think of when you say Arduino, is the ATmega 328. So that one has one 8-bit CPU. Okay, and it runs less than 20 megahertz and has 32 kilobytes of flash memory. This processor, this ATmega 328, uses 9,000 times less power than the Raspberry Pi processor. It's crazy, right? I mean, imagine that. I mean, if you had the Raspberry Pi hooked up to a battery that lasted one day, this guy would last 9,000 days on the same battery. It's an incredible difference in power consumption. In terms of performance, this Arduino is 136,000 times less performant in terms of gigaflops per second. Now, there's other ways to measure performance, but this is, my approximation. Okay. Now, that's kind of strange because you would think that if it's 9,000 times less power, it ought to be 9,000 times less performance. But no, it's 9,000 times less power and 136,000 times less performance. That sounds kind of strange, right? Why is that? Well, if you take the Raspberry Pi and you compare it to the most powerful computer in the world, which is the Summit supercomputer at Oak Ridge National Lab, that has a 200 petaflops per second, uses 10 megawatts of power, and it has 2.4 million processor cores. That's the biggest computer in the world. The Raspberry Pi one Raspberry Pi uses 700,000 times less power than Summit, but it's 7 million times less performance. So you see the same thing happen, right? The reason for that, and this is something I've observed in the work we've done in the lab, is that in general, as you make a computer use less power, as you scale down its power requirement, it also becomes less power efficient. So the Arduino is 15 times less power efficient than the Raspberry Pi, and the Raspberry Pi is 10 times less power efficient than Summit. So that's kind of the trade-off you make, is that it turns out that bigger computers are actually, you wouldn't think it seems counterintuitive, because bigger computers use a lot more power than smaller compact computers. But the bigger computers give you more bang for your buck. They give you more performance per watt of power. And that's just the price you pay to have an ultra low power, lightweight platform. And that's just, that's something you got to deal with. But you don't really have a choice if you need something that's very lightweight. So why did we choose this Atmel ATmega 328 over the Raspberry Pi or any of the many other types of lightweight embedded systems? Well, basically it was to make it harder, to make the course more challenging for you to learn more. The ATmega doesn't have the benefit of Linux or any operating system. You can't run Linux on this processor. So when you write your code, you're writing it on bare metal, meaning that you're writing code that doesn't have the benefit of an operating system. You're essentially writing the firmware for the system, which means that you have to write your own device drivers, meaning you have to write code that interfaces with hardware more closely. You don't have an operating system to do that for you. You also have to manually manage the system resources, like memory, and the peripherals that are available on the chip, and off-chip peripherals. And also, the performance is obviously very limited. So you're going to have to write code in a way that is aware, that is performance aware. In other words, you may have to tune your code a little bit to make it meet certain deadlines required by the application or by the device, the peripheral, the I/O device that you're communicating with. You might also be aware, though, that the Arduinos are often programmed with this Arduino IDE. In fact, you probably use that in 2.11. If you're, I think you've all taken 2.11, I assume. I think, yeah. It doesn't matter if you're electrical engineering, computer engineering, you would have taken that. So the Arduino IDE was designed as with this built-in abstraction layer that allows you to write code that you can write one code and run it on any platform that is Arduino compatible, even if those platforms have different processors. Like some may have Atmel processors and other ones may have ARM processors, right? Maybe there's even MIPS processors in some of these things. In fact, I think MIPS came out with an Arduino compatible.
There was one, and there was also the Galileo was.
Oh, right.
386.
Yeah, Intel had the Galileo, and there was more than the Galileo. There's the Curry, Edison, yeah. So the Arduino IDE is designed to allow you to. It's kind of like easy mode. It's kind of like training wheels, but it does give you the ability to write one code and run it on multiple platforms. I found, though, personally, that it usually gets pretty hairy whenever you use anything that's not an Atmel chip, because you have to be careful with which libraries are included, and in other words, I had an experience where I was using the Intel Galileo, and I was doing this IR controller. And so everyone says, oh, IR is really easy to do on Arduino. You just download the IR library and you just write a few lines of code and you can do IR, infrared, right? So I did that and it didn't work, and I found out later it was because the library was built with all of the hardware-specific features of the Atmel, and it didn't support the Galileo. In fact, none of the Arduino libraries supported the Galileo. So they advertised it as working, but if you're doing anything that did any kind of I/O, the code that you wrote in this IDE didn't work on the Galileo. So we're going to be, instead of using that, we are going to be using the command line tools, and we'll be using the AVR compiler and the AVR libraries. So that way we can just write C code in the text editor of your choice, and then we'll be giving you some make files that you can use that will compile that for the AVR chip, and it'll allow you to program the AVR chip. You guys with me? All right. And so, as with any embedded system, you write the code on a standard desktop workstation, and then you compile it using a cross compiler, which is a compiler that will take your code and will convert it into a binary form that is designed to run, that won't run on the Intel machine you're using to write the code, but instead it's intended to run on another architecture, another processor. And then we're going to use this debugger, this box, to program the code on the Atmel, on the ATmega over a USB cable. You guys with me? And so you might say, well, do we have to do all that? The only way we can run our code is if we have this box and the Arduino board sitting next to us. And yeah, the answer is yes, because strangely, I don't know if they exist, but there's no virtual way to run this code. You have to actually run it on the board. There's instruction set emulators, but I don't think they emulate the peripherals, and certainly not the external peripherals, right?
That is the problem, is that if you are interfacing with, say, a screen, there's not really a way to do that. But there is one that claims to support all of the built-in peripherals, but I haven't tested it yet, and it looks a little complicated to set up.
Well, that was a student project too, wasn't it? Or it was,
somebody's master's degree, basically.
Yeah, no one's, there's no, like AVR, Atmel, the company that makes the chips, they don't provide, like, as far as I know, there's no way to do this, to run it, to simulate it. Yes?
313, we use the Texas Instrument one, the FPGA is the reason why we're not using that board last year.
Oh yeah, so yeah, so he's asking about my other courses, 313 and 611. We use FPGA boards. So similar idea, except those boards are bigger and more robust. We're just doing this to differentiate this course from that course. So in 313, we use an FPGA, a programmable logic device, that allows us to build our own embedded system on chip architecture, basically. So you design the hardware and then you write the software for it. In my 611 course, we use the same FPGA board, but we design the processor from the ground up. So we literally design the processor from scratch, and then we program an assembly language. In this class, we're starting out with this Arduino chip, and we're focusing instead on software-hardware interfacing. Whereas in that, we didn't do much of that in the other two courses. So this course is really, you can think of this as an interfacing course, but it's also, you know, a course that focuses on programming very lightweight systems, right?
And if you remember in 313, right, there was the magic button that says generate the BSP that has all the code to make all the different devices work. Yeah, you're going to do that this time for this course, so that's kind of the big difference.
Yeah, there was in the 313, for those of you that haven't taken it, there was an abstraction there for you where you could have a printf in your code, and you could have a print to the little LCD screen on the board. And it's like, well, that's cool, but like, how's that work? I mean, how did the chip physically talk to the LCD screen? What did the signals look like? Well, that was unclear because that was just abstracted away. In this class, we're going to focus more on those kind of details. Okay. So what about this processor? What's the deal with it? Well, you guys are familiar with MIPS. You learned MIPS in 212, and if and when you take 611, we use MIPS in there. And even in 313, we also use MIPS, although in that case we use a C compiler, so you don't really see it too much. But the Neos processor we use in that class is also MIPS. Obviously, you're familiar with Intel processors, and you know that's the desktop laptops, servers use the Intel architecture, and then your phones and your tablets use ARM. So this is a totally new instruction set architecture for most of you, and even for me, to be honest. I'm just getting into this now myself. So this is an 8-bit architecture. What does that mean? It means that the data path in the chip is 8 bits wide, which means that the ALU accepts 8-bit inputs, which means that you can do any arithmetic operation in one clock cycle on 8 bits. I should say, you can do any 8-bit arithmetic operation in one clock cycle, right? The registers, the general purpose registers, are also 8 bits wide, right? But that's the only thing that are 8 bits, right? So it turns out that the instructions, the machine code instructions, are 16, most of which are 16 bits. There's even some that are 32 bits wide. The addresses, all of the memory addresses used, are 16 bits wide. So in order to store a memory address in this architecture, you actually use a pair of registers. It requires 2 registers to store a memory address, which makes sense because if you were restricted to only one of these registers, one of these 8-bit registers for memory address, you'd be limited to 256 bytes of memory, addressable memory, right? So obviously that's not going to work. So there's 3 pairs of registers called X, Y, and Z that are used for addressing. Most instructions execute in a single cycle, but that's not entirely accurate because what's really happening in this architecture is you fetch an instruction in one cycle and then you execute it in the second cycle while you fetch the next instruction. So it's a 2-stage pipeline. What does that mean? Well, it means that generally speaking, it's 1 instruction per cycle unless you have a branch, and then you still get hit with the control hazard, if you remember that from 212 and in 611. So branches will still be costly. Also, some instructions like multiply, and believe it or not, all the load stores require 2 cycles. So there's a stall that's going to follow every multiply and load store, as well as any branch or jump instruction, right? So you're not necessarily getting 1 instruction per cycle. There's also a status register, which is a little different from MIPS. This is kind of a lot of architectures had status registers. I think Intel still does, technically. But the RISC architectures sort of did away with it because status registers introduce more dependencies in a pipeline. And so first of all, what do I mean by status register? Well, there's these flags in here that get set depending on the outcome of the most recent ALU operation. So you have flags for carry and sign bit and overflow and negative and zero that gets stored in this status register. And then you can use the status register to determine whether or not you should branch, right? You can use it as a condition for branching. However, there's this other bit, bit 7 is the interrupt enable, which is important because you'll be using that that's a way that you can turn off all interrupts just by flipping that bit in the status register. So in other words, all of these bits are kind of the status from the most recent arithmetic operation, but one of them is used to control globally disabled interrupts. All right, so this is also kind of unique because this ATmega architecture uses a Harvard architecture, which means that it has two separate address spaces. It doesn't have one common address space like most computers have. It has one memory that is just for your program, which is a flash memory. It's an on-chip flash memory though, which is kind of crazy, right? There's a flash in the processor, which is odd, right? I mean, there's no other processor that has that. You don't have that in an Intel processor or an ARM processor, right? There's an on-chip flash that's written whenever you program it. Whenever you program the chip, this internal flash gets burned. And the nice thing about it is it's non-volatile, meaning that unlike the FPGA boards we used in 611 and 313, when you disconnected the power and you plugged them, and you reconnected it, that everything would be clear. The program would be clear. These chips will retain the program even after you disconnect the power. And it's kind of crazy. They claim that the data will be retained on there for 100 years as long as you maintain this thing at 25 degrees Celsius. I think it's 25 years at 100 degrees. So there's pretty crazy claims there about the data retention. But that memory is only accessible through your program code, and you can also store lookup tables. If you want to do fast lookups, you can store that in the flash. So in other words, if you wanted to build a lookup table that would approximate like a transcendental function, like a natural log or a sinusoid or something like that, you could store that in the flash and just access it like a lookup table. There's also a 1 kilobyte EEPROM, which is very similar to a flash in the sense that it is a non-volatile memory. But the neat thing about that one is it's a separate memory and it's preserved even when you reburn the main program flash. So you can store stuff in there and it'll stay in there even when you reprogram it. However, it's very expensive to access. It requires four cycles to read and actually 5 cycles. There's 4 stall cycles to read and 3 cycles to write it. And then finally, there's that should be 32 kilobyte. I guess I left the 3 out. 32 kilobyte on-chip SRAM, which serves as the data memory. So that's where you'll have your stack being the place where all your local variables are stored, as well as your function calls, as well as any global variables that you allocate in your program will be stored in the RAM. One of the challenges of writing code for such a small, limited processor is being able to fit everything you need inside that small RAM. So yeah, I don't know why I said it should be 32 kilobytes. I'll have to fix that.
So the on-chip SRAM is 2 kilobytes.
Oh, it is 2. Oh, sorry, I got that backwards. The 32 kilobytes is the flash. Yes, you're right. Thank you. 2 kilobytes is the SRAM. That was right. Yeah, I got that switched. The 32 kilobytes is the flash, and the 2 kilobytes is the SRAM. So there's the memory map of the data memory. The first 32 locations in the memory are actually the register file. The register file is addressed as if it was memory, right? Then following that, you have 64 I/O registers, which are the status and the control registers that are associated with all of the on-chip peripherals, which I'll talk more about here in a minute. Then there's 160 external extended I/O registers, and then the internal SRAM starts at address 256, which is 100 in hex, right? And it goes all the way down to 2FF. Make sense? All right. So this is, oh, that was the pipeline. I already talked about that. Okay, so there's, as I mentioned, they have the chip has these onboard, on-chip peripherals that are built into the system on chip. Most embedded processors are system on chips, meaning that they have a CPU, but then they have a bunch of other peripherals and I/O interfaces on the chip. This one's got an oscillator, like a clock signal. It has external and internal interrupt sources, which we'll be using extensively in the course. It's got 7 different power modes that you can switch. There's the one that it's in by default is active, which draws 0.3 milliamps. But there's these other states where you can put in low power mode. You can also operate these different voltages, 1.8 volts to 5.5, although depending on what speed you run it at, you're more limited in what voltage you run it at. So you can run it up to 20 megahertz, but you have to be between 4.5 and 5.5 volts. We're actually running these at 16 megahertz. I'm not sure why we're doing that instead of 20, but
28P that we're using only goes up to 20. It's a binning thing, so it depends on the.
But we can go to 20, right?
Not ours.
Oh, okay.
You can get a higher grade chip that you can run at a higher clock rate. So like I think all of the 1284Ps run at 20 megahertz, and then some of the lower end chips will only run at 4. So
Okay.
the 328P, you can buy it in models that will support other.
Yeah, because I got this out of the data sheet, so I know the 328P will go up to 20.
Maybe ours are graded for that, but I mean, in any case, the boards we have, the oscillator is 16 megahertz.
Yeah.
So that's kind of just been kind of the standard that people have used for this chip for long enough that it's kind of what people have done. I mean, the 4 megahertz doesn't make much difference.
Yeah, so we're running at 16 megahertz, and we're running at 5 volts, right? This does introduce some complications because some of the external peripherals that we want to use run at 3.3 volts, so we'll have to build in some voltage level shifters for them to talk to one another. So the other things that are on chip, this is kind of a block diagram that tries to show all this stuff. There's 2 8-bit counter timers and 1 16-bit counter timer. We'll be using that to do performance counting and also pulse width modulation. There's 6 PWM channels. There's a 6-channel 10-bit analog to digital converter. I don't believe we're going to be using that this semester. It's got 1 hardware USART interface, which is a serial interface for console I/O, and also you can use it to communicate with certain peripherals. We'll be using that for both console I/O and talking to the external Wi-Fi module. There's an SPI interface, which stands for Serial Peripheral Interface, and there's 1 I2C interface, and I don't even know what I2C stands for. Do you know what that means? It's an I/O. It's a standard I/O protocol.
I know it's a Philips thing, but I don't. It means something.
And actually, Atmel calls this is the 2-wire interface, TWI. So you may refer this you may see this referred to as TWI instead of I2C. There's a watchdog timer, an analog comparator, and an interrupt or wake up on pin change, which is kind of cool. This allows you to put the chip into a low power state, and then whenever one of the input pins changes, it'll automatically wake up. Yes?
I think I looked this up like a year ago, but I think the I2C is a way you can talk to multiple like different peripherals on one of the two wires?
Yeah.
So you can index through them?
Yeah, that's what it's for. I was just wondering what it meant. I was wondering what the acronym was. It's IIC. But it's, we'll be using that for that purpose. We're using I2C to talk to the sensor accelerometer. And SPI we're using to communicate with the screen, the LCD screen. Okay, so this is another unique thing about this chip, which surprised me when I first looked at it. Normally, when you look at the pinout of a processor, most of the pins are to interface with an external memory. So they're usually like DRAM signals. But when you look at this one, and this is the package that we're using. A lot of times when you have an Arduino, it'll be like in a DIP package, a dual inline package. We're using this one that we bought for the kits that you'll be using that are in this quad flat no leads package. So it's this smaller form factor that has pins on 4 sides. So there's 8 pins on 4 sides. There's 32 total pins. There's generally about 32 pins, depending on the package on these chips. But when you look at the pins, you notice that you don't have an external memory interface. So there's no DRAM interface on this thing at all. Obviously because it relies on its internal memory. And also, all the pins on the chip, except for these 8. So you'll see there's 2 power, 2 ground on over here. There's another ground, and then there's analog, reference, and analog power over here. So aside from these 8 pins, all the other pins are part of 3 general purpose ports, which are labeled B, C, and D. I don't know why there's no A. Each one of these is 8 bits wide, except for C, which is only 7 bits wide. I don't know why. But the neat thing about these things is that they are GPIO pins, basically. They allow you can set the values of these ports directly from your code fairly easily. But most of these pins, I think all of them, most if not all of them, have alternative functions as well, depending on what peripherals you activate on the chip. So for instance, if you look at, actually let me go to the next slide, I show it a little better. So if you look at the board, this is what the board looks like, and there's these headers. There's 4 headers that are part of the standard Arduino header form factor, which is a standard interface so you can plug things onto it as shields. But if you look at, one of them is just all like power supply and ground. The other 3 generally match up to the ports, the B, C, and D ports. But each pin on those ports has these other functions. Like for example, port D, bit 2 and bit 3 of port D correspond to interrupt 0 and interrupt 1. So in other words, you can use them as GPIO, or you can use them for these like external interrupt pins. Likewise, like over here on port B, you've got a group of them that correspond to the SPI interface. So if you want to do communication with an external peripheral through SPI, you would use those pins, or alternatively, you can just use them as GPIO. Right? Does that make sense? So what determines that? Well, if the data sheet shows a block diagram of these pins. Then they can be input pins or output pins, so they're bidirectional. So you can see that this is the input side where data can flow in through this synchronizer eventually onto the data bus. And then you've got these other paths for output. But you notice that they've got these muxes and they've got these buffers, these tri-state buffers, meaning that you can turn on or off these paths, which eventually lead out to the pin, depending on what you want to do with the pin. So in other words, they're reconfigurable. They're a lot like pins on an FPGA, like user I/O pins on an FPGA. which is kind of neat. Now, the one that I noticed, the important one to look at here is this mux right here, which is controlled by this PVO-EXN signal, and that allows you to choose between this input and this input. So if you're using this for a general purpose I/O or output rather, like if you want to write something, if your software wants to put a bit on this pin, it would go through this input on the mux, which would be overridden only when this signal gets asserted, which only happens when you start to use that pin for its alternative function, and it happens automatically. So I was kind of freaked out by this when I first started looking at this. I was like, I'm going to have to go in and write this big initialization section to configure all the pins before my code runs. That's going to be a pain. But it turned out I never had to do that because I was able to use, if you use them as GPIO, they just work as GPIO. And if you use them for their other purpose, like if you tell them to do an SPI transaction, they'll just automatically and transparently switch over to that function, which is kind of cool. I didn't believe it till I actually tried it. Now that's for the output. Now for the input, you'll notice that there's this, right here, there's this fan out point, right? This wire goes through this amplifier here, and then it gets fanned out. One part of it goes through this synchronizer, and the other part of it goes directly out to this DIXN output. The DIXN is connected to whatever the alternative purpose of the pin is, if it's used as an input. Like, so for example, the interrupt pins, there's two interrupt pins, this signal would go to the interrupt logic, and then this allows you to still read it out as onto the data bus. So in other words, I could be using this as an interrupt pin, but then I can issue a load instruction that would allow me to access the state of that input pin through the data bus in my code. Does that make sense? So in other words, you can read the value of all the pins, all the input, all the pins, treat them like inputs, even if they're being used as an input for some other hardware feature on the chip. Does that make sense? It's kind of obscure, but I think you'll understand this a little better once you start writing code for this stuff. So in this slide, I went through and tried to map out, because it wasn't, one of the things I don't like about the silk screening on these boards is that it's not really clear what these pins are if you just look at the board. For example, they have this section called analog in, A0 through A5. It's like, well, how does that match up? There's only 3 ports. There's B, C, and D. None of them are called analog in. Likewise, they've got these 0 through 7 digital, and then they've got this one that goes 8, 9, 10, 11, 12, 13, and then ground, AREF, SDA, SCL. I couldn't figure out where these things were going to, because in the architecture, they call them just port B, port C, and port D. None of these names that they have in the silkscreen exist actually in the data sheet for the chip. This is all just manufactured by the Arduino people. So this board happens to have an open source PCB design on GitHub. So I went to that PCB design and I cross-referenced the traces coming out of the chip, and I traced each one of these guys to their pin to try to create this lookup table so I could figure out, like, for example, digital pin 4 is what inside the actual Arduino. Well, it turns out that is the PD4. So port D, bit 4. Also, the alternative function is counter 0 source if you're using the counter and you want to use that as a source for your counter 0. Likewise, analog pin A3, what does that match up to? Because there is no analog pin 3 if you look at the data sheet. Well, that's this red box, and that's actually port C, bit 3, which also can be connected to the analog to digital converter bit 3 if you're using that. But if you're not using an analog digital converter and you just want to use that as a regular GPIO pin, then you would be using port C bit 3, right, inside your code. Does that make sense? Yes?
So are the SD and SCL pins also actually the same as A4 and A5? Because those are both
The SD...
at the bottom of the
These guys. Yeah, so,
Those are PC4 and 5, and then PC4 and 5 are also over in the red section.
oh, did I screw that up? I might have screwed that up. PC, that's probably supposed to be, well, B, I don't know. Actually, you know what? I think those might be shorted, actually. Yeah, I need to go back and double check that. I remember that when I was building this, that there was a weird thing where they had them shorted. Can you check that for me? I think those are actually shorted. Yeah, that's a good question. The orange, yeah, SDA. So the SDA, so these guys are labeled SCL, SDA. That's part of I2C, or the two-wire interface, which I believe match up to PC4 and 5, which also are over here on the analog side. So, yeah, Charles will verify that. It might be a typo, but I think that might be, I think they may just be shorted. The other thing I noticed when I was building this is that PB6 and PB7 are not connected to anything on the header. Likewise, PC6 is not connected to anything on the header, although that pin is used for reset, so I think they actually connected it to a reset button. There's a reset button up here where you can press that button. I think they connected that button to PC6, port 6. Port C bit 6.
No, PC5 is ADC5, SCL, and PCN13. So it's actually also an interrupt pin as well.
Yeah.
An SDA is ADC4, SDA, and PCN12.
Yeah, so they're shorted. Yeah, so some of these pins in the header are shorted to one another. Okay. All right, great. Any questions about that so far? Okay. So let's talk a little bit more about these I/O pins and how you read to them. So software, when you're doing software hardware interfacing, there's really just three ways that software and hardware talk to one another. There's programmed I/O, which is where software will execute a load or store instruction that resolves to a special address that doesn't map to memory but maps to a peripheral, meaning that they're mapped to a control register or a status register. So in other words, there's certain ranges of addresses. In the case of this chip, its address is 20 in hex, which is 32 in decimal, right? And it's the 64 addresses starting from address 32 or 20 in hex. All right, those don't map to memory. They map to these registers that allow you to control or monitor hardware. Right? Now this could, generally speaking, in this case, they are either pins that allow you to go off chip, or they are internal peripherals, which are circuits that are on the chip, but they're separate from the main data path of the processor. You guys with me? Obviously, in a chip like a larger scale chip, like the one in your laptop or your phone, it works the same way, except these ranges of addresses are much bigger, much wider. There's a larger block of memory that's reserved for these I/O addresses. Make sense? So what's the problem with that? Well, okay, there's two issues with programmed I/O. One is that it's up to the processor to interact with those addresses, right? So what happens when the peripheral wants to do something, wants to take the onus and do something on its own without the processor necessarily being ready for it? Well, in that case, you would use an interrupt. So interrupts are ways for an I/O device to get the attention of a processor, to interrupt whatever it's doing, and to force it to go to a specific address in the code called an interrupt handler that forces the processor to then go through programmed I/O and query and figure out what's going on and what it needs to do to respond to that interrupt. Make sense? And then for the higher performance processors, you also have DMA, which is whenever you need to do a high speed transaction between memory and an I/O device. But we don't have that capability in this chip, right? So the two ways that you interact with hardware are programmed I/O, meaning that you read and write to special memory addresses, and interrupts, which allow you to write code that is executed whenever a certain event happens related to an I/O device, right? And so pretty much that's going to be the whole semester, is doing programmed I/O and writing interrupt handlers mostly. We'll also be debugging those things using a logic analyzer and lab equipment and a debugger. But generally speaking, talking to hardware and doing hardware-software interfacing is all about just this programmed I/O and interrupts. So what's the difference between a status register and a control register? Well, there's not, it's kind of a, status register in general is when you read an address in order to determine the state or flags that are set by an I/O device, whereas a control register is when you write to a register to control a peripheral. In other words, so status, you can think of that as an input, and a control register is like an output, right? Now in this chip though, there are some registers that are actually broken down into some bits are status bits and other bits are control bits. And you actually saw this even in the status register, right? The status register has 7 bits that are set from the ALU, not an I/O device, but the ALU. But then there's a bit that the user is supposed to be setting. So you have kind of a mixture of inputs and outputs even in one register. And some of the I/O addresses are like that as well. So how do you then, these registers are mostly comprised of individual bits that have a specific purpose, or ranges of bits like fields that have a purpose. So whenever you access one of these control registers or status registers, you have to do something called bit twiddling, which means that you have to access, read and write specific bits, as compared to do what you're used to doing, which is treating a word or a variable value as just one monolithic value, right? You guys, like in Java, you declare something as an integer. You generally don't look at the individual bits of that integer. You just use it as a number, right? But when you access these control and status registers, you need to interpret specific bits for specific things, right? So how do you do that? Well, basically you use shift instructions and bitwise logic operations. I should say shift operations, because we're gonna try to stay in C in this class. We're gonna try to not have to go to assembly language. So when I say shift instructions, I really mean shift operations in C, right? Likewise, bitwise operations are also a concept in C and in Java as well, right? You guys with me? So you might have been wondering, I remember in 212, when I used to teach 212, that students would often, whenever I would cover shift instructions and these bitwise logical, sometimes someone would ask, like, when would we use this? What is this useful for? Well, this is mostly what you use that kind of stuff for, is this bit twiddling. So for example, this is I made up a register, an I/O register, which is 8 bits, bit 7 down to 0. Now, the most significant bit 7 is on the left, the least significant bit 0 is on the right. So the bits are labeled up here, and then below each bit is a symbolic name for that bit or that bit range. And this is how, when you look at the user guide, the data sheet for the processor, it represents all of the I/O registers this way, right? So bit 7 is halt, and for example, it might say you set bit 1 to halt if you want to stop. Or bit 6 is a status bit that's a flag that it's for on fire. It tells you if the chip is on fire. Bits 5 down to 3 are temperature, which is a code, a 3-bit code, which means 000 is cold, 001 is toasty, 010 and 110 are reserved. A lot of times they'll do that. They'll have reserve values. Why? That's because they didn't have anything to use, so they just say, well, they're reserved, they're reserved for possible future use in another version of this chip or another iteration of this architecture. Meaning that you're not supposed to use those values. And then 111 is white hot, right? So usually you'll have a header file provided to you that has constants declared in the form of pound define for these for the register name, which in this case is PNTLS. I forgot what that's supposed to mean. I forgot how I came up with that, but it's made up. So the register is called PNTLS, and then each one of these fields has its own name. And all of those things are defined in a header file. So if you want to access this thing, generally speaking, you'll get the name of the register and the fields from the data sheet, from the documentation. And then in your C code, you just use them because they will be defined for you with the header files that you will include. Header files meaning, the file that you include, you pound include it. So if, for instance, I want to set the halt bit, the way I would do that is I would say PNTLS equals, right? So I'm assigning the PNTLS register. Then you say PNTLS bar, that's a bitwise OR, means I want to take the current value of the register and I want to merge in, I want to be able to set a bit in there. And in this case, I want to set a 1-bit, but I want to put it into the halt position, right? Now the halt position is bit 7, and you could just say 7, but it's when you start putting what Charles would call that a magic number, meaning it's a constant that you put in your code that it reduces the readability, because as you read it, you're like, well, why 7, right? It makes it hard to read. Also, if for whatever reason you wanted to change which bit was halt, like if you had another chip or something where halt was a different bit, it would be easy to change that if you just use the symbolic name for that. So you take a 1, and I would use this left shift operation. So this would take the 1, it would shift it 7 bits to the left, and then it would OR that in to the register, and then it would. So in other words, it would OR, meaning if that bit was 0, it would make it a 1, or if it was a 1, it would still make it a 1. It wouldn't change it. And then it would set it back to the PNTLS register. Make sense? Right? So that's how I would set a bit. If I want to read a bit, let's say I want to read a flag, I want to read the on fire flag. For that, it's actually simple. You can just use a bitwise OR operation. You would take the 1, again, you'd have to shift it by the on fire, which would be 7, right? So you take the 1, you shift it 7 bits to the, sorry, not 7, 6 actually, on fire 6. You'd shift it 6 bits to the left, and then you would do a bitwise AND to mask off that specific bit. You guys with me? Now once you do that, what is the answer you're going to get? Well, you're either going to get a 0 if the original bit wasn't set, or if it was set, you're going to get a value of 2 to the 6th power, right, which is 64, right? Now you might want to say, well, wait a minute, so I'm going to get a 0 or a 64? Yeah, but remember in C they don't have a Boolean type. In C, a 0 is a false, right? If you're looking at if you're treating a variable as a Boolean value, there isn't really a Boolean value. It's an integer, which is either 0 or non-zero. So even though you're going to get a 0 or a 64 in the C language, that really corresponds to false or true, right? So if you're using that as part of an if statement or a condition, it would work. You wouldn't have to worry about fixing it up, so you would have a 0 or a 1 in there. You guys with me? Yes.
But if you're going to continue using it for other bit twiddling, then you need to.
Yeah, if you want to insert it into another register, you'd have to. Yeah, that would be a concern then. Yeah, you may have to fix it if you use it for something else. But if you're just using it as a true or false, then you can leave it like that.
Something else that's probably important to point out here, right, is that you might be going, well, isn't that 2 operations, right? Because you've got a left shift, and then you've also got an OR, and then you've got a set, so that's going to be like 3 instructions. It actually turns out that the ADR instruction set has instructions for doing things like reading and setting a single bit, and ADR GCC just has enough magic compiler juice in it that it knows what you meant and will drop in those instructions. If you're not sure and you're not trusting it, then you can also read the object dump, which my makefile has a make main.lst that'll print out the assembler for your code. But I thought when I first started doing ADR stuff, I was like, wait, isn't this wasting like a couple of cycles? But nope, actually ADR already thought of that.
I didn't know that. It's a good point. Any questions about that? Now, by the way, notice that there's this temp. I put this temp in here, which is short for temperature, not temporary. It's actually multiple bits. Sometimes you'll have multiple bits, right? So the temp will actually be 3, right? You just have to shift by whatever the lower number is in the range, right? Okay, any questions about that? Okay, now it gets a little bit more complicated. This is just kind of a summary. Like what happens, for instance, if I want to turn a bit off? Like this would turn on the halt, right? It puts a 1 bit there, right? What if I want to put a 0 bit in there?
Change that 1 to a 0 in the first one and then make it an AND statement instead of an OR.
Well, what you'd want to do is, if I want to set it to 0, there's a couple, well, let's see, a couple ways. I think if you do it that way, if you do an AND, right, if you mask it, you'd want to make sure that there's a 0 in this bit position when you AND it, right? But you want to make sure that all the other bits are 1s, right?
Why
So
you want to make sure that this is 0 when you AND it.
well, because you just want to flip that 1 bit to 0. You don't want to blow away the other bits,
okay.
right? So one way to do it would be to AND it with, you could do the shift, right? Like you do here. And then you could invert this. You can complement this, with the tilde, right? So that way, what you're ANDing it with would, instead of like here, you're ORing it with 1 0 0 0 0 0, right? Or actually, well, I'm missing 2 because that's 3 bits, right? But 1 and 7 zeros, right? That's what you get with this, right? With this shift. But if you ANDed it and you wanted to make it a 0, you'd want it to be 0 and then 7 1s here, right? Which means that you can take this and you can complement it and use an AND, right? But there's other ways you could do it too. Like you could do a NAND with 1. You can bitwise NAND it. Because if you do a bitwise NAND with 1, if you have a 1 and you NAND it with 1, it makes it a 0, right? Well, of course, the problem there is that if you have a 0 and you NAND with 1, then you get a 1. So that would just flip the bit. It wouldn't necessarily set it to 0. Right? Probably the easiest way to do it is just to shift it, complement that, and then AND it. Okay. Okay, let's see here. How much time do I have left?
Pretty close.
5 minutes. Okay, so instead of moving on to the next topic, I'm going to switch back here. I didn't get through the whole syllabus yet, so let me finish that, and then we'll be done. So if you go back to your syllabus, I've got the grading structure on there on section 8. These labs may get rearranged a bit. We're still finalizing the labs, but the topics should remain the same, but we may rearrange the order a little bit. If you go to section 9, if you have any documented disability, make sure you contact the Office of Disability Services. You can arrange for accommodations. Syllabus change policy. As I mentioned, this course is experimental. My other courses I've been teaching for a while, and they've sort of stabilized. But this one is this is the first semester for this new version of 3.17. So expect some changes, but we'll give you notice. We'll give as much notice as we can if there's a change in like say the number of labs, for instance. And because if that happens, we may have to change the weights. Yes.
It says on the grade instruction that there's in-class quizzes. Did you say if those are like announced or unannounced?
They will be announced. Yeah. We're still nailing that down, but we'll probably end up making most of them on Moodle, right?
I think that's usually easier for all of us, I think.
Yeah. The Moodle I found is nice if you can do like multiple choice. It works out nicely because you can just, you do your answers and then you get the grade back right away. We may do in-class quizzes if we want to ask more complex questions, like write code segments and that kind of stuff. So, but we'll let you know. It could be either one, but they will be announced. Electronic resources. I mentioned we use Dropbox. We'll be posting a lot of stuff on there. You will be, like I said, you'll be in project teams of 2. We don't allow groups larger than 2. But you should be aware that you need to work out a way with your partner where you're going to share your code. It's not a good idea to just have both partners log in with the same account. You probably should have like a GitHub repo or Dropbox or something like that. I highly suggest you work that out, and you should also back your code up too. I can't tell you how many times we've had groups that have like lost, for whatever reason. A lot of times it's because they went over their quota. There's a quota system, but no one knows how big the quota is, and if you exceed it, there's no warning. What'll happen is, if you go over your quota, and it's usually just because of the Firefox cache, it's not even that you're downloading videos. It's just, oh, you did too much browsing with Firefox, the cache is too big, you're over the 2 GB quota, and then when you save your code in a text editor, and text editors do this thing where whenever you hit save, they open the file up for writing first, which wipes your file, makes it a 0-byte file in Linux. Automatically, that wipes your file out anytime you open a file for writing. And then they dump the buffer out. Well, when they dump the buffer out, the operating system comes back and says you can't do that, and then you just end up with a 0-byte file. So make sure you back up your code.
Don't forget the prereq thing.
Oh yes, yeah. Okay, yes. I will also post we have another issue too where the courses you've taken for prerequisites sometimes can vary wildly in what was covered. I think you guys probably know that, right? I think that's so. Like some of you might have had a really good, strong, 212 course, and others of you have maybe didn't, right? So, and we're always having this issue where there's sometimes a mismatch between what we expect you to know for this class and what you might have learned. Also, the transfer students, like sometimes a lot of students have transfer credits and they took the prereqs at another institution. We are going to post, actually I already have posted it for section 1, I just have to do it for section 2, a prerequisite quiz, as well as the answers, to give you an idea of exactly what we expect you to know in terms of the architecture and programming and the systems level stuff, okay? So we'll have that. I'll send an email out to remind everyone about that.
And that's not graded, just to be clear.
It's not graded, right? I think that's about it. Everything else is pretty boilerplate. If you have any questions, feel free to email us. We'll see you back here in 2 weeks. Remember, class is canceled next week, and lab is canceled this week and next week as well. Thank you.